Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all in today's session. Well, to access the notebook for today's session, you can access my course page on my personal website, arifpad.me. The other way is to download all the notebook files from a course GitHub account, Arif PUCIT. And all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.3 of the 6th module, Overview of Machine Learning, for the course titled Tools and Techniques for Data Science. Well, my dear students, we all know by now that at a very abstract level, machine learning is the application of AI that gives the machine the ability to learn without being explicitly programmed. By understanding the relationships between the input features and maybe the output label of the given dataset, and then formulating that relationship in a mathematical form. My dear students, in the last session, we have understood the math that works behind simple linear regression in a step-by-step fashion. First, we understood the sum of squares as a cost function and saw as how we can minimize it to drive the formula for computing the slope and y-intercept for the best fit line equation to be used for regression. Later on, we practiced the math that we learned on a toy dataset and finally used some metrics for linear regression to evaluate the model without using any function of scikit-learn library. My dear students, if you have not watched that session, I strongly recommend that you should watch that first and then fall back to this. Let me move on to the agenda of today's session. So today, first we will have a quick recap of the previous session. Then I will give a 5 minutes brush up session on solving system of linear equations using matrices, as we will be requiring that knowledge for multiple linear regression. And after setting the stage right, I will start by answering the what and the why part of the question. That is, what is multiple linear regression and why we need to do multiple linear regression. After that, we will dive into the math of how to do linear regression involving multiple independent variables. And of course, we will drive the formula to calculate the regression coefficients by minimizing or differentiating the matrix representation of the sum of least square cost function. At the very end of today's session, we will apply these concepts using a sample toy dataset. So we have a lot to do today. So let's start playing. My dear students, before I move on to multiple linear regression, let us have a quick recap of our previous session in which we discussed in detail about simple linear regression. And most of you must be knowing by now that in simple linear regression there exists only one independent or feature or predictor variable based on which we want to predict or forecast the value of a dependent or a label or maybe a response variable. And this table shows some real life examples of simple linear regression. The linear regression model is actually a mathematical relationship or a function that maps the input features to the output label. And in case of a single feature variable, this mathematical relationship is a line equation, which can easily be visualized in a two-dimensional graph as shown over here. In our previous session, we discussed in detail as to how the salary package of a graduated student is dependent on his or her CGPA. With these four sampled pair observations, we somehow try to fit the best fit line, which is a line that passes as close to all these points as possible. Well, the line equation is y is equal to beta naught plus beta 1 x, and maybe if it is not passing through all the points exactly, we might have a error component as well over here. Well, this beta naught is the y-intercept, which is the minimum value of the response variable, that is salary over here, and the value of the minimum value is roughly 40k as shown over here. And similarly, beta 1 is the slope of this best fit line, and is actually the weight that is multiplied by the value of the predictor variable, that is CGPA. And together this beta naught and beta 1 are called the regression coefficients. In the previous session, we discussed in detail as to how we can calculate these two regression coefficients, beta naught and beta 1, by minimizing this loss function or error function, which is the sum of squares due to error, that is SSE, and is calculated by the sum of squared distances between the actual point y and its corresponding predicted point y hat, shown with these red lines over here. The goal was actually to find out those values of beta naught and beta 1 for which this error function give us a minimum value. And of course we did that by calculating the partial differentiation of the error function with respect to beta naught and beta 1, and then later equating it to 0. Anyway, finally we arrived at this closed form solution of finding beta 1 and beta naught, shown in red over here at the bottom. And my dear students, this is called closed form solution, which is actually a mathematical expression involving constants, variables and operations like addition, subtraction, multiplication, division and so on, but no limit, differentiation or integration is involved over here. And if any differentiation or integration is involved, then this is called non-closed form solution. And of course we will talk about the non-closed form solution in our next session of gradient descent. Anyways, my dear students, these two formulas, they are used to compute beta naught and beta 1 in case of single feature or single independent variable. And if we have more than one input features, the derivation of the formulas for beta naught, beta 1 and beta 2 and so on, maybe they will become quite complex. So another way of finding the values of these regression coefficients is by using the perspective of matrices and using the matrix algebra. And of course this will also be a closed form solution, as we will be deriving a formula but using matrices this time, that will minimize the same cost function, that is minimizing the sum of squares of the residual distances. And that is why of course this solution is called the least square solution. Well, the advantage of using the matrix perspective, which we will do today, is that we will derive matrix formulation to compute regression coefficients for both simple as well as for multiple linear regression. So let's start with multiple linear regression, and before we jump on to that, let me give a quick recap of a portion of my linear algebra video session which deals with solving system of linear equations using matrix algebra. Interested students can watch that portion from this link over here. Well, most of you must be knowing that linear algebra is actually a field of mathematics that deals with vectors, matrices, system of linear equations and linear transformations. We have already studied that a system of linear equation can be written in a matrix form as Ax is equal to B, which is shown at the top in green, where A is a matrix that is known, B is a vector that is also known, and we try to solve for x, which is unknown. Here A is a matrix of size n by m, where n is the number of linear equations while m is the number of unknowns. My dear friends, if n equals m, then this A will be a square matrix. Moreover, if A is a non-singular matrix, that is a matrix having non-zero determinant, then we can find the inverse of this matrix A, and thus can calculate the unknowns using this second green equation, x is equal to A inverse B. And I have discussed different techniques in my LA session to solve system of linear equations for a square matrix, that is when the number of equations is equal to the number of unknowns. And the methods we discussed over there are Gaussian elimination, Cramer's rule, and simple matrix inversion. My dear students, in machine learning literature, instead of this Ax is equal to B, you will normally come across the equation x beta is equal to y. So instead of a known matrix A, we have matrix capital X. Instead of known vector B, we have vector Y. And instead of unknown vector X, we have vector beta. In real world scenarios, we mostly have overdetermined system of linear equations, where the number of equations is greater than the number of unknowns. And of course, in that case, we get a thin and tall matrix X. And at times we have n less than m, which is an underdetermined system of linear equation. And in that scenario, we get a fat matrix X. So to conclude, the matrix X in most real world scenarios is not a square matrix. And the problem is how to calculate its inverse. And once again, in my video session of linear algebra, I have discussed different techniques to solve overdetermined system of linear equations having known square matrix X. And the techniques I think I discussed over there are Gauss-Jordan elimination, Moore-Penrose pseudo-inverse, and I think I talked about SVD, QR, and Cholesky decomposition as well. Last but not the least, the system of linear equations in real-world scenarios are mostly inconsistent. That is, they have no unique solution, and therefore we have to find the best approximate solution. My dear students, if the last 4 minutes discussion was all Greek to you, I strongly recommend that you should make time and click this link and understand these concepts. And if you have a fair idea of it, let me move ahead. Okay, my dear students, a single independent or feature or predictor variable can rarely explain the dependent or response or output variable. For example, the GPA of a student cannot truly be predicted by just the number of hours he or she has studied daily. It also depends on many other predictor variables like the teaching aids, the instructor qualification, the lab facilities, and so on. And this is what multiple linear regression is, which considers the effect of more than one feature variables on some outcome of our interest. And this table shows some real life examples of multiple linear regression. My dear students, we can easily extend the simple linear equation to multiple linear regression equation, and it can be generalized to this last equation shown in green over here. where y hat is the value of the dependent or response or the output variable. These x1, x2, x3, so on to xm are the values of m feature or predictor variables. These beta 1, beta 2, beta 3 and so on to beta m are the weights that quantify the effect of respective feature variables on the output variable. And finally, this beta naught is a constant term that represents the minimum value of y when all the feature variables are 0. So remember, for m input features, there will be m plus 1 regression coefficients. So beta 1, beta 2, so on to beta m, and this beta naught as well. So what we need to do is, given a data set that is a lot of x's and their corresponding y's, I need to use the ordinary least square technique and compute the best possible values of these regression coefficients, beta 0, beta 1, beta 2, so on to beta m. After somehow learning the values of these betas, you give me a new vector x, that is x1, x2, x3, so on to xm, containing the values of all these input features, and I can easily predict the corresponding output value of y hat by substituting those values over here. One more thing, my dear students, in case of single input feature, the mathematical model is the equation of a line, that is y hat is equal to beta naught plus beta 1 x1, which of course we did in our last session. In case of two input features x1 and x2, the model is the equation of a plane, that is y hat is equal to beta naught plus beta 1 x1 plus beta 2 x2, and can of course be visualized using a three-dimensional plot. However, in case of three or more input features, the model is the equation of a hyperplane, which is a bit difficult to visualize as we the human beings live in a three-dimensional world. However, the generic form of a multiple linear regression is shown in magenta color over here. And of course, this is linear because all the betas are raised to the power of 1, not 2 or 3. Okay, so fine. Now we have a fair idea about what is multiple linear regression. And before we learn how to do multiple linear regression, let me touch upon two related concepts. One is the multicollinearity and the other is overfitting. Let me use this simple data set for this. Let me load this toy data set from a CSV file into a pandas data frame. So this is a data set having 10 observations or data points having three input features x1, x2 and x3 and the output variable y. All these three input features will be utilized to explain or predict the value of the output variable. I hope this makes sense. Let me quickly talk about overfitting. My dear students, adding more input features blindly to your dataset does not mean that the prediction will be better. Rather, it can make things worse and may cause a problem called overfitting. And overfitting is caused by adding too many feature variables which account for more variance, but actually add nothing to the model. And such model fits too tightly to the existing data, and the chances are there that it will not fit well on the input data that the model has not seen. So in order to decide whether to keep a feature variable in your dataset or not, you need to check the relationship between each feature variable and the output variable. And this can be, of course, done by calculating the Pearson correlation coefficient as well as by drawing the scatter plot between each feature variable and the output variable. I have done it over here on this dataset. You can observe that this x1 and x2, they both are having a strong a linear relationship with y. X1 and y, they have a linear relationship The correlation coefficient is 0.928. X2 and Y, they again have a strong correlation coefficient of 0.916. On the contrary, this third graph on the right shows that there exists no relationship between the input feature X3 and the output variable Y. And this can be seen visually in this scatter plot, as well as you can confirm this from the value of the correlation coefficient, which is 0.267. Let me describe this by assuming that suppose this Y is the GPA of a student, and this X1 is the study hours, and this X2 is the instructor qualification, which of course have an impact on this output variable Y. And let me say that this third input feature X3 is the height of the student, and naturally height of a student has no role to play in the prediction of a student GPA. So this X3 will just add more variance. Therefore, we can always drop it from the dataset. So to summarize, my dear students, before you use multiple linear regression model, you must ensure that there should exist a linear relationship between the dependent variable and all the independent variables. I hope this makes sense. Another point we need to check out before we use multiple linear regression is that there should be no linear relationship among the feature variables themselves. And once again, this can be checked by calculating the Pearson correlation coefficient and drawing the scatter plot. So here are the three scatter plots. This left graph shows relationship between x1 and x2. The middle graph shows relationship between x2 and x3, and this right graph shows relationship between x1 and x3. Well, this left graph shows that there exists a linear relationship between x1 and x2 with a correlation coefficient of 0.956. So adding both these in our model will cause problem of multicollinearity, as the algorithm will not be able to decide as what coefficient to assign to these two variables if they are so similar. On the contrary, this x2 does not appear to be correlated with x3, and similarly this x1 and x3 are also not much correlated. So to summarize, we can say that in a perfect scenario, all the input or feature variables should be somehow correlated with the output variable. But the feature variables should not be correlated with each other. The violation of first rule will cause overfitting, while the violation of second rule will cause multicollinearity. My dear students, I think now the stage is set to learn as how to do multiple linear regression. In our previous session, we have derived the formula using least square method to calculate the value of beta naught and beta 1 in case of a single feature variable. In case of two or more feature variables, deriving the formula using the same technique becomes a little bit more complex. So the matrix algebra comes for our rescue. Well, we have already discussed the generic form of multiple linear regression, which is shown in magenta color over here. For m input features and n data points in our data set, this summation can be expanded to these overdetermined system of linear equations as shown over here. Let me describe these two comma separated subscripts of x. Well, this first equation represents the first data point, and at this first data point we have x11, x12, x13 and so on to x1m. Well, this first value 1 represents that this is the first observation or first data point, and this second value represents the feature. So there are a total of m features. So this is the value of the first feature for first observation. This is the value of the second feature for the first observation. This is the value of the third feature for the first observation, and so on. And similarly, in this last equation, we have xn1, xn2, xn3, and so on to xnm. And the first value n shows that this is the nth observation or data point, and the second value 1, 2, 3, so on to m shows the feature values. And of course, we can write these n equations, system of overdetermined system of linear equations having m features in a matrix forms as shown over here. Well, this right matrix can also be written as a product of two matrices as shown over here. You can note that by multiplying this first row with this column, we get this. This 1 is multiplied with beta naught, this x11 is multiplied with beta 1, x12 is multiplied with beta 2, and we sum them up and we get this first expression over here. I hope this makes sense. Well, this matrix X is a n by m plus 1 matrix, n rows and m plus 1 columns. My dear students, it has m plus 1 columns because of the additional intercept, which we take as 1 over here. In matrix X, once again, it is important to understand that these subscripts, you can think of it as xij. Xij entry represent the ith row and the jth feature. And this notation you need to understand, it provides a very elegant way to organize, index and access a lot of data. And finally, this can be simply written as y is equal to x beta. And this y hat is actually a n by 1 matrix or an n dimensional column vector. This beta is a m plus 1 dimensional column vector. And of course, this x is a n by m plus 1 matrix. Okay, my dear students, for a single input feature, this is the matrix representation given n observations or data points, and in this case we just have to find two regression coefficients, that is beta naught and beta 1. I hope this makes sense. Similarly, for the two input features x1 and x2, this is the matrix representation given n observations or data points, and in this case we have to find three regression coefficients, beta naught, beta 1 and beta 2. And my dear students, if we have all the values of these betas, and of course I have all the x's and the y's, I can easily predict. If I don't have a y, you give me these betas, I put them in this equation and I can easily compute the value of y. Now a $100 question is, given a data set, that is we have matrix x and y, how we can compute these betas? Well, from our background knowledge of vector spaces, we know that the solution to this overdetermined system of linear equation y is equal to x beta. This will exist if and only if this vector beta is in the column space of matrix X. But in case of inconsistent system of linear equations, this vector beta will not be in the column space of matrix X. So we actually project vector beta onto the column space of matrix X and then we try to solve it. I think I have also done this in my linear algebra video session. Well, today let us try finding the best possible solution using the least squares method, as we did in our previous session of simple linear regression, but this time we will use the matrices algebra. So with this background of matrices, let me move on to the intuition. So before I drive the formula for calculating the betas, let's have intuitive understanding of the cost function for multiple linear regression. My dear students, consider this three-dimensional graph. We have two input features, x1 and x2, and the output variable y. With the two predictors and one response, the least square regression line becomes a plane, as shown. Suppose x1 is the study hours and x2 is the instructor qualification and y is the corresponding GPA achieved by the student. These red dots represent the actual or true values, while the corresponding points on the plane represent the predicted values. And once again, we need to minimize the sum of the squared vertical distances between the actual observation shown by these red dots and the plane. And if we somehow find the minimum of this error function for betas, then this plane is called the best fit plane to the data using least square. So now we have the intuition, that is, we want to minimize this error. Let's do it. Okay, so here is the system of linear equations for the residual errors. So this is the error for point 1 or data point 1, for data point 2, for data point 3, and so on to data point n. And we can write it in a matrix form as shown over here. So this is the column vector E. So this is the column vector Y and this is the column vector Y hat. And of course this can be written as E is equal to Y minus Y hat. As done in a previous session of simple linear regression, we need to minimize the least squares criteria, but this time using matrices. So the residual sum of squares can be rewritten as this. So you can say, you can take the square of this, and this can be written in matrix form as E transpose times E. And substituting E is equal to Y minus Y hat and expanding this transpose, we come up to this equation number 1. I hope this simplification makes sense to you all. Well, in equation 1 over here, if we substitute y hat is equal to x beta, we substitute y hat is equal to x beta in this equation 1, we come up to this equation, and if we just multiply these two terms, we come up to the equation number 2. So this is simple multiplication. My dear students, we know that A transpose B whole transpose is equal to B transpose times A. So in this equation 2, we can write this Y transpose X beta as X beta whole transpose Y. These both are equal. So by substituting this over here in this equation 2, we come up to this equation 3. My dear students, I strongly recommend that you should do all this using a paper pencil. I hope this will make sense once you will do it using a paper pencil at your own time. Well, as with the least squares method for scalar values, over here as well, the goal is to find the value of this vector beta that minimizes this error. And for this, we need to perform matrix differentiation. We need to do matrix differentiation with respect to the vector beta and equate it to 0. If you know how to calculate the derivative of a matrix, it is great. However, if you don't, Then to keep things simple, these are the four formulas that we can use to differentiate this equation number 4. Let me describe these. Suppose that y is a n by 1 vector, x is a m by 1 vector, and A is a n by m matrix. If matrix A is independent of vector x, then we can use the following formulas for this matrix differentiation. Uh, Consider this matrix equation y is equal to A. If we differentiate with respect to x, of course we get a 0 because this will be treated as a constant. Similarly, for this equation, matrix equation, y is equal to ax. If we differentiate with respect to x, we get matrix A. I think these two are simple and straight. For an equation like this, y is equal to xa. If we differentiate with respect to x, we get A transpose. And for matrix equation, y is equal to x transpose ax. If we differentiate with respect to x, we get 2x transpose times A. So using these formulas, uh, the first term over here becomes 0 because there is no beta over here, and this becomes 0. This second term of equation 4, uh, this second formula is applied. So we get minus 2y transpose times x. For the third term of equation 4, we use this fourth formula and get 2 beta transpose x. So after differentiating this equation 4, we get this equation 5. Now in the remaining steps over here, I have used simple matrix operations and have finally arrived onto this matrix equation shown in red, that is beta is equal to x transpose x whole inverse x transpose times y. So this is a formula to calculate the regression coefficients in case of multiple linear regression. So once I have this vector beta, all the betas, you give me a set of x's and y's. I calculate the betas using this red equation, and once our model has learned all the regression coefficients, we can use this equation over here in magenta color to predict the value of y. Let me repeat this part. You give me all the x's and the y's, all the data points. I put them in this matrix equation, this formulation. I get a vector of all the betas. Now I have all the betas. You give me any set of x's. I put them in this equation shown in magenta color and get the predicted value of y. My dear students, once again do note that if we have m input features, there will be m plus 1 regression coefficients, with beta naught as the constant term that represent the minimum value of y when all the feature variables are 0. I think great job done. Let us now do multiple linear regression on a simple toy dataset to apply what all we have learned today. That is this equation. Okay, let's read this CSV file and load the dataset in a pandas data frame. Okay, so there are a total of 200 rows or observations and 4 columns with 3 input features and an output column, sales. My dear students, this is an advertising dataset showing sales of a product in 200 different markets along with the advertising budgets for the product in each of these markets. for three different media: TV, radio, and newspaper. Our goal is to develop a machine learning model that can be used to predict sales on the basis of three media budgets. So you give me new budget for TV, radio, and newspaper, and I can predict the sales. So this is our goal. And one thing I missed to mention are the units of these columns. The values under the TV, radio, and newspaper columns are in thousands of rupees, while the values under the sales column are in thousands of units of that product. I hope the data is making sense. Okay. Let us first check out if there exists a relationship between the three advertising budgets and the sales. And we know this can be done using the scatter plot and correlation coefficients. Well, the code of this cell, just don't worry about it. It's just a repetition of the things. It just used NumPy's methods to compute the correlation coefficient that we did in the previous session as well. The new thing is that over here I have used this subplots method of pyplot module of matplotlib by specifying the number of rows and columns, and this method returns a figure object and axis objects in tuples with one tuple for each row in grid. Then I have simply used the scatterplot method of Seaborn by passing it the x, y, the data frame, and the axis object. So I hope this makes sense. Let me execute the code of this cell. So this is the output. So you see these are the three graphs that shows that the advertisement on TV has the most impact on sales of the product because this is more linear. While the advertisement on newspaper over here has the least impact on sales. So this is the linear relationship. You can visualize this. I've also calculated the Pearson correlation coefficient. You can check this out. So the newspaper and sales correlation coefficient is 0.228. I hope this makes sense. Okay. Now let us check out that the feature variables should not be correlated with each other, and this can of course be done by drawing three scatter plots among the three input or feature variables. And this is the same more or less piece of code that do this job. Let me execute this. And these are the three graphs between the TV and radio. This left graph, totally random. And this rightmost graph between TV and newspaper. They are also not correlated. However, this middle scatter plot shows that radio and newspaper has a moderate positive relationship with a correlation coefficient of 0.354. I think that is negligible, that we can keep all these three variables in our dataset for the time being. So there are no issues of multicollinearity as well as overfitting. Let's move ahead now. Let us now create the output vector y from the sales column of the data frame. I have just used the sales column of this data frame, converted it to a NumPy array. So this is a NumPy array having 200 values of the sales column. So this is our vector y. Let us now create a feature matrix, and this can be done by just this dropping of the output column sales from the data frame. So let me execute this. So you see now we have a matrix having 200 rows of course and just 3 columns. So this seems to be great. Now just one more thing we need to do is we just need to add an additional column of ones in this feature matrix to create the actual X matrix of size 4 by 200. And this can be done by using the numpy insert method by passing it 4 arguments. The first is the name of the 3 by 200 feature matrix as above. The second argument is 0. This specifies the column index where we want to insert the new column. And since we want to insert the new column over here, so we have placed a 0 over here. This third argument specifies the value, which is 1. And of course, the fourth argument specifies the axis along which we want to insert. Let me execute this. And you see we have our matrix X, which is a 200, having 200 rows and 4 columns. This is the exact X matrix we need. So we have m plus 1 by 200. M plus 1. M is 3. So this is 4 columns and 200 rows. Great. Remember, this M actually represents the number of features. Well, another way of creating matrix X from the feature matrix is you just create a matrix of ones using np.ones method and then use a numpy hstack method. So this can also be used. This is also a piece of code that you might come across. Anyway, we have got the matrix X as well as the matrix vector Y. Great. So now we are ready to compute the regression coefficients. And to compute the regression coefficients, this is the formula, which is beta is equal to X transpose X inverse times X transpose times Y. And this is what we have derived above. So the remaining task is a simple math. We can always do it in one line, but I have just shown that over here I am just multiplying, taking the dot product of X with Tx. You can use this formula, or you can use this. So the dot product of X transpose with X. So this is X transpose times X. So we get a matrix, symmetric matrix of size 4 by 4. So in order to calculate the inverse of this matrix, we just use the inverse method of the linear algebra module of NumPy library. So this is the inverse. Once again, a symmetric matrix of size 4 by 4. And now let me calculate the dot product of X transpose with Y. So this is it. And finally, over here in this cell, over here, I have done it all in one line. Let me just execute it. And here are the 4 regression coefficients: beta 0, beta 1, beta 2, and beta 3. Well, the negative value of beta 3, that is the weight of newspaper advertisement, shows that it do not have a positive relationship with sales. So it is better that we drop this newspapers column, as it is adding nothing to our data set. So now we have all the regression coefficients. We are ready to carry out the prediction. Let us predict the expected sales for the advertisement budget for 180 for TV, 10 for radio, and 58 for newspaper. I've just taken random values. You just substitute this vector of x1, x2, and x3, the 3 values of the 3 features, into this equation, and we already know the value of beta naught, beta 1, beta 2, and beta 3, and we can easily calculate or predict the value of y. And this is what I have done over here. Great. So the predicted sales for this feature vector, that is 180, 10, 58, is 13.002. That is, if you spend 180,000 rupees on the TV ads, 10,000 rupees on the radio ads, and 58,000 rupees on newspaper advertisements, you will be able to sell 13 units of the product. Great. My dear friends, now that we have trained our model and used it for prediction, it is time to check its accuracy. So let's move ahead. In the previous session of simple linear regression, we have talked about cost function for linear regression. And in simple words, it is the difference between the actual value and the predicted value. It determines how well our model is predicting for a given data set. The lesser the cost function value, the more accurate is our model. While more the cost function value, the less accurate is our model. We of course talked about mean absolute error, mean squared error, and root mean squared error in detail in our previous session, whose formulas are shown over here. In the last session, we also talked about the R2 score, also known as coefficient of determination, which tells us how much variance in the dependent variable can be accounted for by observing the variance in the independent variable. And the most common formula to compute the R2 score is 1 minus sum of squares due to error divided by total sum of squares. And we also discussed the different values of the R2 score, which can range from 0 to 1. For example, a value of 0.75 means 75% of the variance in the dependent variable is accounted for by observing the variance in the independent variable. My dear students, a limitation of R2 score is that if you add more features to your model, the R2 score will increase or stay the same, but it will never decrease. This adjusted R2 score is actually a modified form of this R2 score. And the value of this adjusted R2 score increases if new predictors tend to improve model's performance, and the value of adjusted R2 score decreases if new predictors do not improve performance as expected. You can calculate adjusted R2 score using any of these three formulas, which all will of course yield the same result. And let me explain this formula given in green. First of all, remember that adding a new feature is a loss of 1 degree of freedom, and of course that has its cost. And in this formula in green, this n represents the number of observations, while this m represents the number of input features. Let me show you how adjusted R2 score will decrease when you add an irrelevant feature. This R2 score in this formula on the right side will remain same, so the numerator will remain same, but since m increase by increasing the feature, so the denominator will decrease. Therefore, this overall second term will increase. So when you subtract it from 1, the overall adjusted R2 score will decrease. I hope this makes sense. You can always rewind this half a minute portion and listen it again. Similarly, my dear students, if you add a relevant feature to your model, this R2 score in the numerator will increase, although this m will also increase and the denominator will decrease, but the R2 value will increase more than m. Therefore, this time the overall second term will decrease, so the adjusted R2 score will increase. Okay. And finally, uh, this cell has a sample code where I have used these formulas to compute the evaluation matrix for our linear regression model. Let me execute it. Great. Note the value of adjusted R2 score for our multiple linear regression model is 0.896, which means 89.6% of variance in sales is accounted for the three feature variables. Great job done. Okay. Finally, my dear friends, here is the task for you to do at your own time to check out your understanding of multiple linear regression. Let me load this dataset in Panda's data frame. So there are six feature variables: age, sex, body mass index, children, smoker, and region. And the response or dependent variable is the medical cost billed by suppose a health insurance company. You need to apply today's session knowledge to build a linear regression model. You need to train your model on this data set, and then you need to predict. By dear friends, for this data set, you may have to do a little bit of data pre-processing as well. As you all know that machine learning algorithms cannot work with categorical data directly. And over here you can see the categorical data under this sex column, male and female. Uh, Under this smokers column, yes and no, and under the region column as well. By difference, you can use label encoding or one hot encoding to convert these categorical data into numbers before you feed it to your model. After you have done the pre-processing, you just need to build the model and evaluate it, and hope it will be fun for you all. I wish you all the very best for this task till we meet in our next session of math behind gradient descent. My dear friends, if you have liked this video, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.